Welcome back to our discussion of advanced SQL. Our discussion of data types now brings us to times and dates and timestamps and intervals, the range between two times. And this is really remarkable because the support for time values and date values inside the SQL database system is much richer than what you would normally find in your programming language of choice. Makes sense because many applications out there that are database backed are dependent on time in some form, and the systems deliver really in this respect. All right, so let's see how timestamp, time, and interval support is coming along in PostgreSQL. Okay, so when we are talking about time, this is really what we mean. So there is a continuous flow of time here, and at a particular point, we can carve out a timestamp T1 or a timestamp T2. T2 is after T1, and we can talk about this particular point in time as a value in the PostgreSQL type system. All right, so we've got support for timestamps, and such timestamps are normally comprised of a date component and a time component. And as you can see on these slides, already the date and the time itself is marked in blue here because these in themselves are available and supported types inside the SQL database system. All right, so we can talk about such timestamps. So a particular day that we fix with the date and then a particular time on that day. Or we could just talk about a day, no particular time involved, or just a particular time, no particular day or date involved. So all of these combinations are available. All right, so a timestamp has full information, date and time have just the date and time components. Okay. We can cast between these types, and as you can imagine, we can cast a timestamp into its date and time component. Okay, so forget the other component in a sense. I think that is expected. We can also cast a date into a timestamp. Casting a date into a timestamp just assumes that we are talking about the time of 0 hour, 0 minute, 0 seconds here in this particular case. Okay, so we can convert between these different time-dependent data types in PostgreSQL. And these time data types, timestamp, date, and time, each come with optional support for time zones. So if you take, for example, the data type time and put it here in place where I have the type variable tau, then a time with time zone is actually an internal representation inside the database system of a particular point in time that is aware of time zone support, which makes a difference if you compute the span, the interval between two times in different time zones, for example. So time zone support can make a difference. So these type names like timestamp with time zone is quite a mouthful, so PostgreSQL supports this equivalent shorthand notation for such time zone equipped data types. Intervals represent the difference between two timestamps. Okay, so this is a span of time between two timestamps, the timestamps T2 and T1 in this particular case. And such an interval arises from arithmetics, from the subtraction of T2 minus T1. So this is the time span between these two timestamps. So this indicates already that we can do arithmetics with times. And there is many more arithmetic operations available on these time data types, and I will show you in a minute over in the editor or so. All right. What about the resolution? So I said this is a continuous flow of time, but of course system internal, we have to have some granularity of time representation. And as you can see here on the slide, timestamps, time, and also these intervals are measured to a resolution of 1 microsecond. Okay, so that would be the time resolution inside the system. Dates, of course, have a granularity of 1 day. So Nothing else makes sense there, but these are the resolutions that you can expect in PostgreSQL to be available for you when you compute with times. Okay, so how would one enter and specify times, time literals? And we have already seen that in, I think in 2 videos ago, I've shown you a date literal. So of course we will fall back to the SQL convention of enclosing complex literals, complex constants of types in single quotes, which are then parsed and converted into internal values of the appropriate target data type, for example, timestamps, dates, or times. And it works just the same way here. So if you've got a date literal, then enclose that date literal in single quotes and cast it to date to obtain a real date. The same you can do with times, and the same you can do with timestamp literals. This is actually indicated on the slide here. So enclose the whole thing in quotes, then list the date literal first, then some white space here, and then a time literal, and everything will be converted, parsed, and then converted to a timestamp once you cast this string, this textual representation, to an internal timestamp. Okay, how about time input and output? So how are the parsing rules for date literals, for example? Because from region to region, from nation to nation, from continent to continent, there are different conventions how a particular time or particular date is actually represented in text. And PostgreSQL is really flexible in this respect, because there is a system-wide variable called the date style variable, and date style controls output as well as the input format of common dates. So you see that the date style value is actually a comma separated value with one component in front, one component after the comma. Before the comma, we specify how dates should be output, and the default value would be the ISO format. So it's a Anglo-American inspired output format for dates, but we could alternatively switch to the German format. So the day.month.year format, and we will do that over in the editor in a second. The input format is controlled by one of these values back here behind the comma, and you can see that you can specify that dates that are read are interpreted with month first, then day, then year, or maybe this convention, or maybe this latter's unusual convention, first year, then month, then date. These are possibilities that you can specify to adapt PostgreSQL to your particular notation of dates in this particular sense, in this particular example. All right. Okay, so we can specify times and dates and timestamps using this literal syntax. There's also literal syntax for intervals. So a quoted value that you can see here that can specify years and months, days, hours, minutes, down to seconds, it will be interpreted as an interval value. All right. So some of these fields may not be relevant to you. So you may be speaking about an interval that's just measured in days. So then this would be the only component that is present in your string literal. All right. Fractional seconds can be specified by using a fractional s value for the seconds here. So you can speak of 0.2 of a second by using an interval that reads 0.2 seconds. So quite natural syntax, which will then on casting be transformed internally into an interval. There's quite a number of special literals provided by the system that present particular timestamps or particular dates. So for example, the now time can be interpreted as a date, which would be the date of the current system time, the current system date of the system currently running PostgreSQL. Or we could just use the now timestamp, which would cover the date as well as the exact point in time up to a microsecond granularity of system time. So this would be two possibilities to talk about the present point in time. Regarding dates, we can speak of today, we can speak of yesterday and tomorrow. All of these are convenient, human readable, but also machine interpretable notations for dates. And there is other notations for timestamps. The epoch timestamp, which is of relevance to the Unix ecosystem, which is the 1st of January of 1970, or the infinity timestamp, which would be some point in time in the future, as far pushed back into the future as the system PostgreSQL allows you to represent. Okay, so let's switch over actually to the editor and see how this behaves. All right, so here you can see I'm using this special literal now here and have it interpreted as a date, as a time, or as a timestamp notation. And let's see what the current date is and the current time. All right, here we go. So today is the 4th of May, so it's still Star Wars Day. Yeah, may the force be with you, people. Okay, it's currently 15, 14, 16, as you can see here. So that would be the now interpreted as a time data type. And the timestamp would, of course, combine the two to a complete specification that includes date and time. Okay. As I told you, we can optionally switch on time zone support. So let's look at the now timestamp without time zone support and with time zone support. You can see that I've mentioned the full timestamp with time zone type name here and cast the string literal now into this time zone control timestamp. And we can see the difference here. So this would be the current timestamp, and this would be the current timestamp with time zone support. And you can see that the system is indeed aware of the fact that currently I'm here in summertime in Germany, in the Europe Berlin region, which obeys summertime, and the system indeed knows about that and would incorporate that when I do date and time arithmetics, and we will see an example in a minute. All right. So regarding the output and input formats that PostgreSQL supports, we could use the date style system variable to switch to a different output format. So for example, to the German output format, in which we would represent day dot month dot year in a typical output format. And at the same time, we could select a particular input format, parsing format for our dates. So here would switch to a month, day, here would switch to a month, day, year format, which would be the format that's common in the US and in Britain. Okay, so if this is the input interpretation, then this would indeed be May the 4th, 2020, so it's Star Wars Day, all right. In this other representation, we will still output in German format, but we have to be aware that now the system will expect the day, then the month, and then the year. So this same date literal under this different input interpretation will represent a different day. It's the 5th of April 2020, which is not Star Wars Day and can only be considered very sad. All right, so let's see whether this behaves as expected. Okay, so under this input representation, this is indeed Star Wars Day. Output in German format, this is the 4th of May 2020. Switching over to a different input format using the same date literal here. So please beware of the confusion that can arise. This is just the 5th of April. All right, so before more confusion ensues, let's switch back to the system default, which is just the ISO format in the Anglo-American parsing sequence. Okay. So PostgreSQL is really flexible when it comes to the interpretation of dates and timestamps for that matter. So you can see that all of the rows of this literal 5-row table here would be suitable and reasonable representation of August 26, 1968. Here you see I'm using some abbreviation Here you can see that I'm using dotted notation. Here you can see that I'm using this dash notation and so on, or some slashes. So all of these are out there in the wild. All of these are actually used, and PostgreSQL would be able to parse all of these and would interpret month, day, year, would apply the month, day, year interpretation to all of these formats and would come up with the correct date. As you can see, I'm not bothering to output these here again. What I'm doing is once I casted all of these string values to valid dates, I would then just count how many distinct dates this system has actually parsed, how many interpretations it has found for all of these different string date values, and you will see it only finds a single interpretation. All of these are equivalent. One single interpretation of all of these different formats. So quite some flexibility there, prepared to deal with quite a number of notations that are being used out there. And then, as promised, here are some special date and time constants that you may be using. You don't have to be aware. You don't need special functions to query the current system time and so on. You can just use these nonic string constants to refer to today, yesterday, tomorrow, or these other special timestamps I was already mentioning on the slide. So let's see if that works. Looks good to me. This is the beginning of time according to Unix. This is today, and this will be tomorrow, the 5th of May indeed. All right. Okay, and the same is true for intervals. We can specify intervals, so the difference between two times, the time span between two times, using this extensive syntax here. We could use this quoted value and interpret it and cast it into a valid interval type. As I told you, all of these fields are optional and could be omitted. Okay, and because this is quite a mouthful, there is also the standard ISO notation for intervals, which is much more compact and is understood by Postgres just as well. So let's mark this and let's see whether these two intervals indeed specify the same thing. Yes, they do. So, all right. So much for that. So this would be the specification of times and dates and timestamps, and how can you compute with these? So when you compute with time, you will very quickly find yourself in doing arithmetics on timestamps, like the subtraction of time spans to measure a length of time, to measure the length of the interval, or maybe to add an interval to a particular point in time, just to step a few days or a few minutes or seconds, whatever you have, into the future. All of this is indeed possible. All of this is just specified using the regular arithmetic operations on dates or timestamps. It also makes sense to use multiplication or division on intervals. So it may make sense to talk of now plus 2 times a month, to talk about the timestamp that is 2 months from now. And all of this would be possible in SQL date and time arithmetic. How this looks syntactically is just as expected, I would say. So we could just measure the time that has passed between now, which would be today, including the current time of in the day, and subtract that from yesterday, and we will see that we receive an interval value that could then be printed in the appropriate fashion, and you can see that this would be the 1 day and 17 hours 27 minutes and so on have passed since midnight yesterday. Okay, so the library of date and time functions in PostgreSQL is really extensive, and we will switch over to the editor in a second and play with some of these. But this is just to give you a glimpse of what is possible there. Of course, if you've got a particular timestamp or if you've got a particular date or time, you can extract fields like the hours of a timestamp or the seconds of a time. By using this extract function. You have extra constructors, so non-string syntax constructors that allow you to create dates and timestamps. You can compare these times and see whether two timestamps are equal, whether one date is before another date, and all of this can be very naturally done with just the normal comparison operators. And there's also special comparison operators that check whether two ranges of times overlap. And I think I also have got an example for that. There's also a time of day function, which in fact yields a string, really a text string of the current time on the current day. So please be aware that what you get there is not a timestamp or a time that you can do arithmetic with. What you end up with is just a text value, just so that you know. Okay, so let's see what we can do with date and time arithmetics and intervals. And you can see this is just what I'm doing here. So I've got dates and I've got timestamps. And what's interesting here is that I'm doing arithmetic between the two. Okay, and we will see what comes out of this. This is the current day. This is my retirement date. And what I will see here is the number of days. The number of days that still have to pass until the retirement comes. That's nice. All right. And you can see all kinds of other arithmetic that I'm trying out here. So starting from now, from the current date, and then add 30 days, which is just a special interval without any hour, minute, or second component. This would give me a new date that is just 1 month in the future. Or I could look 2 months into the future, as I've told you just as we were talking about the current slide. Okay, we could check how many hours it still would be until midnight falls. So from now, looked at as a timestamp until tomorrow's date, which would be interpreted as the day of tomorrow at 0 hours, so midnight. So that would be the interval that reveals how much time is left until midnight falls. All right. From such intervals, I could extract particular components, for example, the hours until midnight, all right, as I told you. And if you subtract two dates from another, just as a caveat, if you subtract two dates from another, what you will get is an integer value. An integer value, the number of days between the two dates, all right. If you want to convert this into a true interval, a true interval of that only consists of a day's specification, that would be one way to do it. You can see that there is this constructor syntax supported in PostgreSQL, as mentioned on the slide, and converting this integer that I've just computed based on this date difference is easily converted into a day's difference by using this make interval function. Okay, so let's try that. All right. So 5,596 days until retirement. There's quite some time to go, but I think there's light at the end of the tunnel, I would say. So today in 1 month would be the 3rd of June. Today in 30 days, to be exact. Today in 60 days would be the 4th of July. All right, 8.5 hours until midnight. Extracting from that just the hours component would yield this integer 8 here. All right, the date difference between yesterday and tomorrow is just 2, and converted into proper interval that would be 2 days. So I think date arithmetic behaves just as you would expect. So you can be really flexible, and you can really do some advanced things here, as this highlighted expression indicates. All right, so what else could we do? We could generate all the month M in this generate series, and then use that to generate the 12 first days of a month. So you can say year 2020, each of the 12 months would be considered, and we would just create that first day of the month, of all month in 2020. But from these, we would just subtract 1 day. an interval that is exactly 1 day long. This would yield the day just before the first of the month, so it would yield the last of the month. So this would be one way to check, hey, how many days are there in a particular month? This would be PostgreSQL answer to that. Okay, so 31 days in December, and in January, as you know, 29 days in this year's February. Okay. And so on and so on. This would be one example of date arithmetic. So, all right. Here's a little example that plays with time zones. Okay, so what is happening here? You see that this values table is considering different time zones. All of these would be valid time zone specifications in PostgreSQL. Okay, nice. So what are we doing with that? So actually what we are doing is we consider the actual timestamp currently with time zone support. So this would be the actual current timestamp regarding and including time zone support at the current place I'm operating the system at. Okay, so my system is aware of the Europe-Berlin time zone. Okay, from these time zone values, I'm constructing timestamps that are located in these particular time zones. And how am I doing that? I'm taking advantage of the fact that PostgreSQL or the SQL system is able to convert arbitrary string-based representations of timestamps with time zones, for example, into internal real timestamps. Okay, and that's what I'm doing here. So I'm just getting the actual timestamp here without time zone support, as you can see. And I'm appending a space here just as a separator. And then I'm just adding as a string concatenation operation these time zone values, these particular time zones. So what I'm getting here is a timestamp that I have equipped and augmented with these particular time zone specifications. The resulting string is then interpreted as a timestamp with time zone. All right. So one time the current timestamp in the current time zone of my system. Then the same time zone interpreted as a timestamp in many other different time zones. And this is the difference between the two timestamps. This will yield the difference in hours between the two timestamps, and would give me a table of timestamp differences that I could use, for example, to schedule video conferences, which are so important, sadly, today. So these difference values I'm ordering them so that we get a listing of time zones here that are ordered by the difference to our time zone. Okay, so let's do that. Yeah, I can just take this and evaluate the query. And this is what we got. Okay, so Pacific Standard Time is 10 hours behind, while Asia Tokyo time zone is 7 hours in front. You can see we are really free in specifying these time zone specifiers. We can just work with actual time zone hour differences. We can use these symbolic names, the ISO symbolic names of the time zone names, or we can also use these self-speaking specification of time zones. All of them are interpreted correctly, and all of them can be used to do timestamp arithmetic and extract the difference in hours, measured in hours between the two timestamps. Of course, there's a difference of 0 hours to Europe-Berlin itself. That's where we are located currently. Okay, as a final example, it's a very sad example because it checks whether it's currently holidays for us. Okay, so you can see this would be a table of the current school holidays in Baden-Württemberg, the state of Baden-Württemberg. All right, and what I'm specifying here is just the name of the holiday and the starting and ending date. And this is what I'm iterating over here. All right. And then I'm using the overlaps. I'm using the overlaps built-in function of PostgreSQL to check whether this date range spanned by the holiday start and ending dates overlaps with this particular date range with just today. Starting and ending date of this time range is just today. This represents the single day today. Does today overlap is included in this holiday range? If so, then please print which holiday we are in. So let's see. 0 rows. Okay, this is the 4th of May. Currently no holidays are going on. That's fine. Pentecost would be the next that can hit us, but currently there's none. All right, so that would be an example of the binary overlaps operator that can check date ranges. The support is really extensive, and I can only encourage you to play with it. It really makes the development of applications that are in some way date or time dependent much easier than you normally would find in the normal programming languages, where you would probably have to rely on some external date or time libraries. Okay. So much for date and times. Took some time, but the extensive support, I think, warrants it. All right. So talk to you soon in our exploration of data types in SQL. Bye-bye.